All right. Hello. I'm Pry, and today I was just thinking about making a video on like what a sort of normal college CS curriculum looks like. Uh, I don't know who this would be useful to. Maybe if you're trying to self-study or whatever. But I thought this would be sort of a fun summary about showing what courses people take, why, and why I think it's not a bad system, at least in the way that they're laid out. Um, so first things first, the first thing you'd learn, the first sort of class you'd take is some sort of intro to programming, and it would just be literally any imperative programming language. Uh, I really don't care which one you'd pick. Like Python works, JavaScript works, C works, C++, Java, literally anything. Um, just most people start with an imperative language. You can start with whatever actually, but this is just what most people do. Uh, all of these are good options. I started with JavaScript, right? Then I went on to Java, then Python, then C or whatever. And you can just go in any order. It doesn't really matter. All of these languages are very similar. Um, so, yeah. And I just wanted to include this Dijkstra quote here because he sort of says, "Hey, it's practically impossible to teach good programming to students who have had a prior exposure to BASIC, as potential programmers they're mentally mutilated beyond hope or of recognition and or regeneration. Excuse me, what the fuck? But anyhow, it's I mean, Dijkstra's a genius, right? And he's entirely correct. And yeah, I wonder what this says about me as a JavaScript programmer. Next class you'll take is discrete math. So, discrete math is kind of just most of the math you'll need for CS, barring like I don't know calculus or linear algebra or something if for like graphics. And it's math on discrete structures. What does that mean? Well, here's a bunch of sort of topics you'll talk about. You'll talk about Boolean algebra, which is a fancy way of saying algebra about values of true and false, which are really important because, I mean, you can model a true or false with one bit. You can model it as ones or zeros, right? And so, really, all of computing can sort of be essentially decomposed into just these logic gates, just very basic equations of Boolean algebra. I guess very complex equations, but sort of simple in their rules. What's very interesting is also these sort of and or not gates, these sort of logical operations, are also what can be used to model circuitry, like digital circuitry. And this is actually something that I believe Claude Shannon sort of really sort of popularized. I don't know if he came up with it at first, but it's a very interesting idea. So very important. Set theory. Set theory is really interesting because it's sort of the foundation of mathematics to an extent. And set theory is really all about the study of what a set is. A set is really just a collection of things. That's sort of what you sort of have it be defined as. And it's really fascinating how much you can really, how much of math you can build up from set theory. So discrete math has like a little intro to set theory section. We talk about other discrete structures in it, like lists, trees, graphs, sequences, and so on. These are all very important because these are sort of what we use in data structures and algorithms to model our data. So we learn about the mathematical properties behind these things. Here's some resources I like. I would highly recommend LOGICOMIX. It's all about Bertrand Russell's life and all about the foundations of mathematics. It's amazing. It's a really, really quick, like 1 hour read. It's a comic. Just go get it. It's awesome. As for other discrete math textbooks, the one we used was Rosen's Discrete Math. It's perfectly okay. It's not a good textbook. It's not a bad textbook. It's passable. And a lot of people recommend Concrete Mathematics. I like it, but it might be a little bit daunting at first. I think it's a good textbook, but it might just, I don't know if it's exactly beginner friendly, but hey, if you want to try it out, I think it's cool. Written by Graham Knuth and Padashik. All right. Okay, now we get on to some very interesting class, algorithms and data structures. Um, it's interesting because in certain universities, certain places, algorithms and data structures will be broken up into different classes. I don't really understand that. Or sometimes they'll be broken up into algorithms like one and advanced algorithms or something like that. So it is just a lot of content to put into one class. So that's why it sort of makes sense. But algorithms and data structures really, really go hand in hand. So the resources for this class I'd recommend are the Algorithm Design Manual, really fun book, really sort of almost conversational in its writing style, really good. Introduction to Algorithms, this textbook's also known as like CLRS. It's sort of the standard reference, but it really is just that. It's kind of just a reference. I wouldn't read it cover to cover. It's very sort of a good reference. Algorithms and data structures. I don't think I need to tell you how important they are, but they really are what sort of lead us to write programs that are efficient. And also just lets us think about how do we sort of even go about writing efficient programs? How do we organize the data in such a way that we can do what we want to do? The next class is computer architecture. Also, this is not really, just wanted to say, this is not really a strict hierarchy. You could do computer architecture before you do data structures, I think. Computer architecture is sort of next on my list, and it sort of just fundamentally answers the question, how do computers work? How do computers understand instructions? What does that mean? At the end of the day, we've got semiconductors, and the semiconductors are really good at modeling these sorts of very basic Boolean operations, like and, not, or that sort of thing. How do we get that sort of thing to understand and add instruction, or even decode the instructions that we want? And it's a very interesting and beautiful subject. And just here is sort of like a very, I don't know, sort of complex diagram, right? But it's a very complex subject, and most classes won't go too into depth of it because it's kind of just too much of a field. It really deserves its own like sort of major, right? But it's good to at least understand the basics of it so that you understand how to write highly performant code based on sort of the quirks that CPUs have. There's a lot of optimizations that you can use because of quirks of CPUs. You learn about like caching and this and that. So here's sort of the topics. You'll talk about logic gates at first, the sort of and, or, nor, etc. You'll talk about flip-flops. Oh, I misspelled that. It's a flip-flop, not a flip-flip. And how memory is sort of implemented at the very basic level. And then sort of the final thing that my class talked about is pipelining, which is this sort of architecture through which you're able to get much better sort of utilization of your CPU. I would say that all of these things are extremely complicated and don't exactly sort of match what is in use today, but it's good to know. And stuff like the concept of a memory hierarchy, RAM is pretty expensive compared to like going to your CPU registers and so on, and the idea of caching, like say you have some array and you're looping through that array. If you get the first element of that array, chances are the CPU prefetches a bunch of other elements from that array that are contiguous, and so if you just sequentially run through that array, it's a lot faster than randomly accessing things in that array. That sort of optimization you can learn from this class. Resources. There is an amazing YouTube channel on this topic who goes by the name of Ben Eater. Ben's Beware, right? But he's incredible. He's got this whole series on he's got videos on how like semiconductors even work at like a chemistry sort of level. He's got videos on how to make like the basic logic gates out of transistors, and then he goes from there and he really shows how to make your own sort of computer with a very basic architecture with breadboards and so on. It's really amazing. It's really hands-on. It's really cool. It's very visual, which is nice. So highly recommend just watch all of his videos. And from there, the sort of like, I suppose mainstream, but really honestly, like it's mainstream for a reason. Resource for computer architecture is Computer Organization and Design by Patterson and Hennessy. It's just a really good book in my opinion. I also haven't read too many other resources on the topic, so I could be wrong, but I think it's just a good textbook. It covers all the sort of things you'd want from that sort of beginner intro sort of class. And if you're someone who's interested in more sort of the very, very fun, like deep topics in computer architecture, Hennessy and Patterson also has this Computer Architecture, a quantitative approach textbook, which is essentially just computer organization design, but a lot more in depth. And they go a lot more into sort of more modern techniques, superscalar techniques, this and that. It's very complex, and I haven't really read through it. I've read some of the appendices of it, and just to sort of review myself, and it's really well written, I think. So next class, operating systems. This is a really fun one. Operating systems is a very poorly named class. It's a general systems class is what I actually call it. I think operating systems is more of a historic name, and the reason is because operating systems are a system, so it's a system that we all use, and so it's a good way of sort of framing systems programming. It's also just something that everyone interacts with, so like there's that. And then also a lot of the topics that you'll talk about in OS class were first researched in the context of operating systems. But operating systems is, once again, a general systems class. All of the topics really generalize well to a bunch of other different types of systems, distributed systems, virtual machines, virtualization, all sorts of other sort of technologies. So I would say OS class is kind of difficult. At least in the place that I took it, it was just a lot. So I would say sort of the big topics that it covers: virtualization. How does your computer virtualize resources, virtualize the CPU, virtualize memory? As in, how do you give the illusion of your how do you give programs on your computer the illusion of having the entire CPU to itself, or having a certain chunk of memory to itself, while in reality it's sharing all the resources with other processes, that sort of thing. Concurrency, how do you sort of have all these processes and then coordinate between them? How do you do that? There's a lot of very interesting problems. You'll talk about how do you synchronize between them with semaphores, locks, monitors, all sorts of techniques there. Persistence, I think this is interesting because it's all about sort of file systems. How do you talk to hard disks, SSDs, that sort of thing? And you get into sort of, once again, the concept of this memory hierarchy and trying to go to disk as a few times as possible, that sort of thing. It's very interesting and, once again, very complicated. And just other fun topics you might cover. We talked a little about distributed systems, which I thought was really fun. And we also talk about networks because the operating system needs to have a networking layer. And so that's just a lot of topics, and all of them you could just go way more in depth into. So I would say sort of the best resources for this. There's an amazing free textbook on this online called Operating Systems 3 Easy Pieces, and it's just the best. It's all free online. It's very funny. I thought the textbook was just really, really well written, very it said a lot, but it was never dry, which I thought was very awesome. And if you're someone who wants to actually sort of write your own OS, after sort of going through this, is the OS Dev Wiki. It's this sort of old timey internet wiki that has tons and tons of resources about how to make a bootloader, how to go about structuring various things. It's all of the sort of like technical details that your class almost definitely won't cover. So next class, the theory of computation. This is a really fun one as well. It answers the question, what is computation? What is computable? It really gets to the heart of what is computer science. So let's see. I mean, it's fascinating because this is a very sort of mathy class, and this is the class where you talk about sort of the fundamental limitations of computer programs and computers. We start to try and answer the question, how do you mathematically define computation? And the history behind this is very interesting because Alonzo Church comes up with this definition called lambda calculus in the broader context of trying to solve one of David Hilbert's problems. And around the same time, Alan Turing comes up with this concept of a Turing machine. He called it like some sort of computing machine or something, I don't know, but we now call it a Turing machine. And turns out those two ideas of computation are equivalent. And Gödel, pictured like right here, he sort of said, hey, lambda calculus is wrong. That's not what we should call computation. He comes up with his own sort of thing called general recursive functions, and people show that, hey, that's actually just equivalent to lambda calculus, which is equivalent to Turing machines. And Gödel's like, dang it, I'm incorrect. I couldn't, like, if mine is equivalent to yours, I couldn't possibly be correct, which I think is just funny. But it's fascinating. It's when you get three separate people coming up with the same idea of computation, it feels like there's something to that definition. There's something deeper there. And so we really talk about sort of what we define as computation, and we talk about the limitations of computation. What are things that we cannot possibly do? It's good to know our limits. I would say that another sort of thing that falls into this class is complexity theory. This is a fascinating topic. It's all about sort of, I don't know, the sort of the difficulty of problems. I would say certain different types of problems fall into different complexity classes, and so certain there's the whole sort of like notion of like a P versus NP. We've got polynomial time complexity, and then we've got non-deterministic polynomial time complexity, and so on. And we've got problems like the example of NP is, these are problems that are easy to check we are correct, but hard to compute the answer to. Versus, hey, there's P space, which is problems that are even hard to check if you're correct. So there's all sorts of different classes there. So for resources, I think The Annotated Turing is a really fun read. It's a book that is really just annotations to the original Turing paper. And so you sort of get to read Turing's own words, but with like really helpful annotations that like sort of help you understand what he's really meaning. I thought it really helped. And I would say Sipser's Introduction to the Theory of Computation is kind of just the go-to textbook for this sort of thing. I think it's really well done. I think this is sort of a weird comment, but it's one of the most beautifully formatted books I've read. It's very well done. So I would sort of highly recommend that. Now moving on to some electives. We'll sort of breeze through these because you can just pick whatever, but here are some fun ones that I thought of. There's like going to be surely some that I've missed, a lot that I've missed. Distributed systems. I love distributed systems. I think they're so cool. I don't even know what these guys are. They're having fun. Distributed systems is a very interesting class. It's all sort of about how do we coordinate between systems that are distributed in space, that are separate, that fail independently. So one machine can fail and the other ones can continue. How do we be fault tolerant in such a case? How do we deal with that? How do we think about that? How do we prove things about that? The textbook that my class had used is this Gauche's Distributed Systems. But honestly, I think Designing Data-Intensive Applications is also another really good book. There's a lot of good literature on the space, and it's very interesting because it's for sort of a field that's still in motion. I'm personally looking forward to sort of researching more into this field, learning more about CRDTs. I'm also planning on making a video series on the matter. So if you're interested, sort of let me know what you'd like me to sort of cover. But yeah. Also, this is the logo of Raft, which is like a consensus algorithm. And I don't know, I can't decide whether I think it's cute or horrifying. Functional programming. I sort of mentioned imperative programming earlier on, but there's a lot of other types of programming languages. There's logic programming languages. There are functional programming languages. Some languages that fall into multiple categories. It would be really... I think you'd be missing out if you don't try all of the other paradigms out. And functional programming is one of those paradigms, and it's quite popular. I mean, a lot of sort of front-end frameworks and this and that have taken functional ideas. A lot of even imperative languages are taking these functional ideas because they're, quite frankly, good ideas. So, I don't know, pick up Haskell or Lisp or any of that. I think it's just something that's fun to look at, and probably worth an elective. I would say resources wise, the Little Schemer I've heard is a really good sort of like good intro into Scheme, which is a Lisp. I've also heard that SICP is good. I've started SICP, I haven't finished it, so I can't like fully recommend it yet, but SICP so far is good. And it also is sort of an introduction to Scheme, but probably a little harder. Yeah. Moving on, databases. Databases is also just another amazing sort of topic. Very similar to OS and distributed systems, but there's a lot of sort of systems programming that goes into databases, and every like most programs nowadays use a database of some sort, whether you're using like an embedded database like SQLite, or you're writing a web app that requires the use of like Postgres or something. So I think it's super valuable to learn about the internals of databases, or at least understand the sort of trade-offs that you're making when choosing databases. I don't think that one thing is right. I don't think one size fits all. That's sort of a famous paper in databases. But I would say one sort of fun resource online that's free online is called the Red Book. It's Readings in Database Systems by Michael Stonebreaker. What a fucking cool name. But anyhow, yeah, it's just a good resource. And I would also say, I forgot to include this on the slide, but the CMU Database Group YouTube channel is amazing. And I'll try and add like a link in the description below. But they do amazing videos on the topics. Oh, and AIML. This is sort of a very, very, very hyped field at the moment, but it is genuinely interesting field, even outside of the hype. I honestly don't have too much to say that you already don't know. I would say one of the best books in the field is Stuart Russell and Peter Norvig's Artificial Intelligence: The Modern Approach. That's a really good book. I thought it was outdated, but I looked and they have like a new version that has a lot of the sort of newer sort of neural net stuff, which is really cool. I know that Ian Goodfellow has a deep learning book as well. So if you're sort of more interested in sort of like the mathy side of it, I would highly recommend Deep Learning by Ian Goodfellow. Web dev. I suppose you could, I don't know if colleges even have electives for web dev, but like, I'm assuming they totally do. So the web is the dominant platform nowadays. I mean, it's a good idea to learn it. So here's just a bunch of fun technologies they put on the screen. Yeah. And graphics. Computer graphics are really complicated, and I don't know anything about them. I've heard real-time rendering is a good book, but graphics is something that I'd like to get into at some point as well. Okay, next very interesting topic is compilers. Compilers are, how would I say? Compilers are one of the sort of programs that computer scientists use all the time, and I think it really, really helps if you better understand compilers. A lot of problems end up being compiler problems. Not that like there's problems with the compiler, but a lot of problems that you'd come across in real life could be sort of formulated in the techniques that people who write compilers know how to solve very easily. Some really good resources on compilers is Crafting Interpreters by Robert Nystrom. This is just a free book. And it covers a lot of very interesting topics in sort of like lexing, parsing, that sort of thing. And another famous book in the field is Compilers, Principles, Techniques, and Tools by Aho, Lam, Sethi, and Ullman. And this is just known as the Dragon Book in sort of common vernacular, because of this really cool, like you can tell like effort went into this cover, you know. But yeah, that's the end of my slideshow. Thanks for watching. I should probably script these a little more, but I can't be bothered. Thanks for watching.